As you can tell from the title, it's time for another practice algorithm, so we're going to jump right into it. For this problem, I want you to write an algorithm that's going to determine if any pair of numbers in a list is going to sum to a given value. So we can go ahead and assume that I'm going to give you a list of integers in no particular order, and I'm going to give you some value. And your job is to write an algorithm that will go through that list and determine if any two values in that list sum to the given value. If it does, you return true. If it doesn't, you return false. So I've kind of already given you some hints to your inputs and your outputs, but make sure you understand the problem. You define your inputs, your outputs, your steps. You can either use a flowchart or a more natural language algorithm. And then once you pause the video, you finish all that, come back, resume the video, we'll go over the solution. So go ahead and pause the video now. Okay, so we know that we're going to have a list of numbers, and we want to go through and determine if a pair equals some other value. So we'll go ahead and give ourselves a very basic list here that we can work with, and I'm just going to do a sorted list from 1 to 5. Now it doesn't have to be sorted. I'm just going to write it sorted for now. We know that it will come unsorted, but that may or may not matter for our solution. And let's say we're going to look for a value, and I'm going to go ahead and pick a value that's already in here, and we can see that the value of 7 is in here, and it's actually in here twice. So we have a value 7 here and a value 7 here. So I'm going to pick 7. Actually, I'm going to pick 9. So we only deal with 1. Dealing with 2 might complicate things, so I want to try to find a simple problem to start with. And so 5 and 4 is 9. And there's no other combination, I don't think, in here in terms of pairs that would equal 9. And so that's what I'm looking for. So we need to figure out how are we going to determine if the list contains this pair or not. Well, I could start by looking for a value. So I could take this value and I can say, all right, if I'm looking for 9, maybe the only match here is 8. So let me go through and see if I see an 8. Okay, I don't see an 8, so I know that maybe this isn't going to be a part of the pair. So maybe I do the same thing with 2, and I know that it's going to be a 7, so let me see if I can find a 7. So that might be one way we can consider doing that. Another thing that we might be able to do is just compare pairs. So here's a pair, here's a pair, here's a pair, here's a pair, right? And then there's a pair here between 1 and 3. There's a pair between 1 and 4, between 1 and 5. And so maybe if I just go through and compare all the pairs, maybe I can exhaust the search problem and find it. So that's what I think I'm going to start with. So how do I pick the pairs? Well, maybe I should just start at the beginning and work my way through. So I could maybe check 1 and 2, and then check 2 and 3, then check 3 and 4. But I might lose track of, did I check 1 and 3 already? Did I check 1 and 5? I can't remember. So that might get a little hard to figure out. So maybe I should check all pairs that exist with 1. So 1 and 2, does that equal 9? No. Okay, so does 1 and 3 equal 9? No. All right, does 1 and 4 equal 9? No. Does 1 and 5 equal 9? No. All right, so now I've exhausted all possible pairs that have the number 1 in it, or at least this particular one. So now let me look at all pairs with 2. Well, does 2 and 1? Well, I don't really have to check 2 and 1 because the ordering of the pair doesn't matter, and I've already checked 1 and 2. So I can just keep looking in this direction. So does 2 and 3 equal 9? Nope. 2 and 4, 2 and 5? Nope. All right, so let me keep looking in this direction, but starting at 3. So does 3 and 4? It does not. Does 3 and 5? It does not. So let me look here. 5 and 4, they do equal 9. So yes, that algorithm seems to work so far. So the algorithm that we're kind of working with right now is compare every single pair and return true if you find one that works. Now, I started with the sorted list. Will it always work if the list isn't sorted? So I'm going to take the same numbers and I'm going to make them random. So I'm going to do 2, 5, 3, 1, 4. So we want to make sure that k is still 9. So I'll put k is 9 down here just so we can keep things organized. And we know that 5 and 4 does equal this, so this should result true, but let's make sure that the algorithm that we came up with will work for that. So again, I'm going to start here and work my way over. So 2 and 5, that doesn't equal. 2 and 3, no. 2 and 1, 2 and 4, none of those. So now I'm going to come here and compare over. So 5 and 3, nope. 5 and 1, nope. 5 and 4, yes it does. It does equal 9. So I can end there. I don't have to check the rest of them. Because again, the problem's just asking me, does 1 exist or not? It doesn't ask me how many or anything like that. Good. So what else might we want to consider? We need to consider what potential base cases there might be. So what happens if the list is just 2 elements? Will the algorithm still work? So let's keep looking for 9. Well, this should return false because these do not value to 1. So if we search from here, 1 and 2 doesn't equal that. And if we search from here, there's nothing to compare to. So we've exhausted all possible pairs. So we would return false. Okay. What happens if there was just 1 element in the list? Well, we would search from here and we would see that, well, there are no possible pairs, so we will return false. So all that works. What happens if there are duplicates? Would duplicates matter? So we can check that. And if, let's say we're going to check for 5, just so we know that the value is in here, we would check 2 and 2, that's not. 2 and 1, that's not. 2 and 3, that is. We're good to go. So I think we understand things pretty well. We know that we're going to have some list of numbers that are given to us. We're going to have some value k given to us, and that's what we're going to be looking for. And we're just going to compare every single pair. And if any of these pairs are going to be equivalent to the value that we're looking for, k, then we say true. There does exist a pair. And if we exhaust all possible pairs, then we're going to say false. We could not find a pair that matched. This might not be the best algorithm, but this is a good starting point. We worked through it. We know what kind of works on paper. So now let's get a better understanding, formalize our algorithm. Once we formalize our algorithm, we can double check that it works, and we can go on from there. All right, now that we've worked through the problem a little bit on paper, we want to kind of formalize our understanding. So in order to do that, we want to make sure we know what base cases to consider. And so for this problem, obviously there's the base case of if we have a number of elements in the list. There's if we have the empty list, and if we have a list with 1 element. So the empty list and the list with 1 element are very similar to each other in the sense that there is no way that a pair can sum to any value because there is no pair, right? So we know that for both the empty list and the list of 1 element, we're going to always return false because there is no pair that sums to the value that we're looking for. So we need to make sure whatever algorithm we create will satisfy those. So the inputs that we're going to have might be a list L of n unsorted numbers. I don't have to specify if n is greater than 0 or anything like that because we're going to make sure we handle the empty list and the list with 1 element, or n being 1, within our algorithm itself. So we don't need to put that qualification in our input. An additional input that we need for this algorithm is the target value, and I'm going to call that value k. So our outputs are going to be true if any pair in L sums to k, and false otherwise. So meaning there were no pairs that sum to k, therefore we will return false. So this is our understanding of the problem. We now have worked through the problem and kind of have an idea of what the algorithm is going to look like. We have a good solid understanding. So now it's time to start formalizing the algorithm. Now before I present the solution that I have for this video, I want to point out that this is not going to be the best solution that we could create, and that your solution might look different. I'm presenting a solution that I feel a lot of people are going to naturally draw themselves to, so hopefully this will look like yours, but we'll see in later videos, we're going to revisit this problem, and we're going to see different solutions that are more efficient, and we'll, by that time, understand what we mean by more efficient and how to actually measure that. So for this one, we're going to basically compare every single pair. right? So we're going to go through the entire list. We're going to compare every possible pair there is. And if any one of those pairs equal k, the sum of those pairs equal k, then we'll return true and be done. But if we look at every single pair and none of them sum to be k, then we're going to return false. So you can already see that there's going to be two loops here of some sort. So the way I've presented it here is we have for I from 0 to n minus 1. So basically I'm going from the first element to the second to last element. And then I want to loop for j is I plus 1 to n. So I'm going from the element right to the right of I all the way up to the end of the list, to the last element. And then for each of those pairs that are created with these two loops, I'm going to check to see if L at I plus L at j is equal to k. And if that's true, we'll return true because we found a matching pair that will sum to k. And if we go through all the pairs and these two loops together, we'll exhaust all possible pairs in the list. If we do not return true in any of those comparisons, we then return false. So that's the basic algorithm, and we'll find that it's a very slow algorithm, or it's a very inefficient algorithm, but that will come over the next couple videos when we start talking about efficiency and complexity analysis. But before we move on, I want us to take the time to double check this. So let's walk through a couple of examples and make sure our algorithm actually works. All right, so let's give us a little simple list here. So I'm going to say 1, 2, 5, and 3. And let's say we're looking for the value to be 3. Okay? So we can look at this and instantly know that this should return true because 1 plus 2 is 3. So let's walk our algorithm through and see if we actually get true to be returned. Well, we're going to come in, and the first thing we're going to do is I is 0 and j is 1. So we're going to do L at 0, so 1 plus 2, because that's L at j. Those are going to be equivalent to 3. Therefore, we're going to return true. Okay, so that works. Now let me change the value to 4. So what I'm doing here is I'm testing to make sure we still get true because 1 plus 3 is 4. But I want to make sure that we can actually move through the list a little bit more but still get a proper pair. So again, we start at 0 and 1, so this is 3. That's not equal to 4. So now we're going to check 1 and 5. Now we're going to check 1 and 3. It does equal 4, so we return true and we're done. So good, we know that it will work when the first value is part of the pair. So now let's try when the absolute last pair is what is going to be the proper value. So that's k is equal to 8. So now that's what we're going to look at. And what you see me doing here is I'm trying to think of all the different boundary conditions that might break it, right? Something we didn't think about. So I want to test all those various aspects. So now we come in here and we go 1 and 2, no. 1 and 5, no. 1 and 3, no. So we've exhausted the first loop of the j at 1 plus I plus 1, I plus 2, I plus 3. So now we go back up to step 1, or the I for loop, and now we're at 2. So now we're looking at 2 plus 5, which is 7, no. 2 plus 3, no. All right, so we go back around. We're now at 5. We check 5 and 3, 8. We're good. So that works. Now let's look at a different list of, say, a single element. Well, if we look back at our solution, we see that if I is equal to 0 to n, well, basically, till we get to the end of the list, well, there's only one element in the list. We're at the end of the list. We're not going to go into that loop if we set up that condition appropriately, and therefore we're going to return false, which is fine. Same thing happens if it's an empty list. Now, if you implement it in a way where your conditions are a little wonky, you might get an error here. So there can be some issues when translating from your algorithm to your implementation if you're not careful with your indices. One way you could explicitly show that is instead of having the for loop start at step 1, we can have step 1 being if list is empty, return false. If n is equal to 1, return false. So you're a little bit more explicit in that sense. But that's kind of up to you. Now, let's check another condition where it doesn't exist in the list and we want to make sure. So let's say I don't think k is equal to 10 is in this list. So again, we would check 1 and 2, 1 and 5, 1 and 3, 2 and 5, 2 and 3, 5 and 3, no problem. Okay, maybe you're thinking, what's going to happen if there's duplicates? Is that going to cause a problem for an algorithm? So say we're looking for 4. Well, duplicates aren't going to matter too much because eventually we'll get to that pair that might match 4 for us. So 1 and 2, no. 1 and 2, no. Because 3 is not equal to 4. 3 is not equal to 4. It doesn't matter that we had to check it twice. 1 and 5, 1 and 7, none of those equal to 4. 2 and 2 does equal to 4, so we return true. You might ask, okay, well, what happens if the value is 4, 1, 3, 0? So now here we have 3 pairs that match, right? We have 4 and 0, and we have 1 and 3. But again, the solution or the problem that we're in is only asking, does a pair exist or not how many pairs there are. So our algorithm will still work. 4 and 1 doesn't fit the bill, so we go all the way till we get to 4 and 0. That fits the bill, we return true. We never check 1 plus 3 because we don't need to. All right. Now, if the problem changed and you're asking the question, how many pairs exist, then we would have to modify our algorithm a little bit. But because we're only asking if a pair exists or not, we don't have to worry about that case. So I think we've exhausted most of the boundary conditions here, and I think we've kind of proven to ourselves that the algorithm that we created here does indeed work. As I mentioned, this is not the most efficient algorithm that we could have come up with. We have to end up checking every single pair to determine that there are no pairs. We might get lucky and on the first pair we check it's equal to k, but when we're trying to understand how good an algorithm is in terms of efficiency, we don't necessarily always look at the best case, but we tend to look at the worst case. So in the worst case, there is no pair that matches k. Therefore, this particular algorithm makes us look at every single pair. And if we think about the problem a little bit, we might be able to find a more efficient or a faster way of checking that. And again, like I said, I'm not going to cover it in this video, but once we learn a little bit more about complexity analysis and understanding what we mean by worst case, best case, and the various tools that we can use to analyze the efficiency of an algorithm, we'll revisit this problem and then we'll start comparing different versions of it. But until that point, keep focusing on the characteristics. Keep practicing the way you present your algorithms because, like I said in an earlier video, if we can't present our algorithms well, it's going to be even more difficult to start analyzing how efficient they are in terms of memory or in terms of speed.